Good morning, students. This is the fourth lecture for you of C13 NMR spectroscopy, third semester. We covered about the types of C13 NMR spectroscopy. In that, the first technique is fully coupled C13 NMR spectroscopy, where every carbon of a molecule is able to couple with the hydrogen attached on up to fourth carbon atom, so that each carbon multiplicity, each carbon signal appear with so many number of lines. So interpretation become difficult. That already covered. Therefore, the C13 NMR spectrums were recorded by the spin decoupling experiment. Now, spin decoupling experiment we already discussed about it. And in the broadband decoupled experiment, where all the protons, that is all the protons on all the carbon atoms are saturated at their resonance frequencies, so that every carbon signal is appeared as a singlet signal, and it is a simple spectrum, as we can easily predict the number of signals, number of carbons from the number of signals in the spectrum, and we can also easily interpret the delta value and etc., whatever you need. But when we record the signal, carbon signal, as a singlet, it is lost about the information regarding the number of hydrogens attached by each carbon atoms. That information is gathering, that information is collected from the multiplicity signal. Where in the broadband decoupled experiment, we are recording only a singlet signal, so that not possible to predict the number of protons attached on each carbon atom. Therefore, we have recorded the spectrum by single frequency half resonance decoupled method, that is called as SFORD method. That also we completed. Now in the SFORD method, where at each carbon atom except 1J interaction, that is direct coupling interaction, the remaining all type of interactions like 2J interaction, 3J interaction and 4J interaction between each carbon and each hydrogen is eliminated by the process of spin decoupling experiment, that is double resonance experiment. So that we are allowing every carbon atom to be coupled with the nuclear spin of hydrogen which are directly attached. So in that way, CH3 carbon appear as a quartet, CH3 appear as a triplet, CH carbon as a doublet, and carbon without hydrogen appear always as a singlet. That is called as SFORD spectrum. For example, CH3, CH2, C double bond O, CH, Cl2, dichloro 2-butanone, where this is A carbon, this is B carbon, this is C carbon, this is D carbon. While recording the C13 NMR spectrum, at each carbon atom 2J, 3J, 4J were eliminated by the process of spin decoupling experiment and allowed to couple with only with its own hydrogen, so that the CH3 signal appear as a quartet, CH2 appear as a triplet, CH carbon appear as a doublet, carbon without hydrogen appear as a singlet, like this. A quartet for CH3 carbon, a triplet for CH2 carbon, that is B carbon, a doublet for C carbon, a singlet for D carbon. This is called as SFORD. This is called as SFORD. So up to this part, I completed the topic. Now you have to study few more techniques, C13 types of C13 NMR spectroscopy. That is, now today's class we have to discuss about the leftover experiment, the types of C13 NMR spectrum. That is, the fourth type is selective proton decoupled spectra. Selective proton decoupled spectra. This is fourth type of C13 NMR spectrum. Now almost whatever the information we need from the molecular geometry or structure can be extracted or can be interpreted from the SFORD spectrum. But in few cases, that is, if the frequency difference between any two carbons, if it is too small or too short, then the multiplicity signals in the SFORD get overlapped. Not in all the cases, only in few cases. There are some few molecules where the frequency difference between the carbon atoms in a molecule, if it is too small, the difference is too short, then their signals are appear very near or very close to each other. Therefore, their multiplicity signals might be overlapped sometimes in the SFORD spectrum. For example, you take chlorobromo, chlorobromoethane. This is A carbon, this is B carbon. Each carbon bearing two hydrogen, therefore triplet and triplet. Two triplet signals are appeared. Now you can see A and B. Now the frequency difference between carbon A and carbon B is very similar or very near to each other. There is a difference is very small, short difference is there. Therefore, the two triplet signals related to the two carbons might be overlapped in the spectrum. This is SFORD spectrum. This is SFORD spectrum. Now, when the signals are overlapped, again it resulted a complex NMR. This is a complex spectrum. It is a complex NMR spectrum. We know the interpretation of complex NMR spectrum to get the information is highly difficult. Therefore, where the signals get overlapped in the SFORD experiment, those molecules were also studied by selective proton decoupling method. Selective proton decoupling method. Now, coming to the method. Now, in the selective proton decoupled method, any one of the overlapped carbon is selected. Now, why we are coming to the selective proton decoupling method? Because in few molecules where the carbon frequency is very close to each other, then their multiple signals might be overlapped in the SFORD experiment to get a complex NMR spectra. Therefore, it becomes difficulty to extract or interpret the spectrum to get the information. So, in such cases, the spectrums were also recorded by the method called as selective proton decoupled experiment. Now, in the selective proton decoupled experiment, any of the overlapped carbon gets selected. Any of the overlapped carbon gets selected. And at a selected carbon atom, all interactions like 1J, 2J, 3J, 4J between the selected carbon and between all hydrogens are eliminated by the process of saturation, that is called as decoupling experiment. Are you following? So in this experiment involved selection of any of the overlapped carbon. Means at the selected carbon atom, every interaction between the selected carbon and between the hydrogens of a molecule, that is like 1J interaction, 2J interaction, 3J interaction and as well as 4J interactions were eliminated by the process of decoupling experiment, so that the selected carbon signal appear as a singlet like a broadband decoupling experiment. Are you following? Now at remaining carbon atom other than selected carbon, so selected carbon signals are appear as a singlet at remaining carbon atoms of a molecule, where at remaining each carbon atom except 1J, 2J, 3J, 4J are eliminated like SFORD experiment, so that the remaining carbon signals appear as a multiplet similar to the SFORD spectrum. That is called as, the experiment is called as selective proton decoupling experiment. Is it clear? A simple experiment involved simply selection of a overlapped carbon, so that followed by the elimination of all interactions 1J, 2J, 3J, 4J, and recording its signal as a singlet. The remaining unselected carbon, whatever present in the molecule, removal of only 2J, 3J, 4J, not 1J, except 1J interaction. So the remaining non-selected carbon signals appear with a multiplet according to the number of hydrogens attached with them, and similar to SFORD. So this experiment is called as selective proton decoupled experiment. Example, you take again same chlorobromoethane, where this is A carbon, this is B carbon. Now I am selected A carbon. Before selection, if we record its SFORD, we can see in the two lines, two signal multiplets get overlapped to give complex spectra. Before the selection, if we record its SFORD spectrum, AB carbon two triplets get overlapped. Now I am getting selected carbon A and recorded the spectrum. Now at selected carbon atom, 1J, 2J, 3J, 4J, whatever existed could be eliminated by the process of spin decoupling experiment, so that selected carbon always appear as a singlet. A carbon appear as a singlet. The second carbon, which is not selected, at the non-selective carbon, except 1J, 2J, 3J, 4J are eliminated, so that it appear as a multiplet with respect to the number of hydrogen attached with it. Here it is a CH2 carbon, therefore it appear as triplet. Is it clear? You can see what is the difference between these two. Now in the SFORD, if the signals are overlapped, we are unable to predict type of A carbon and type of B carbon. AB are not known. AB are unpredictable or not known. Coming to the second spectra, you can see B signal appear as a triplet, indicated B is a CH2. B carbon is a CH2. How do we identify? Based on its multiplicity, where when we record one carbon signal as a singlet, automatically the second will be separated, so that it indicated B carbon is a CH2. Now still A carbon is unknown. A carbon nature is not known. It may be CH3 or it may be whatever it may be. Then if we select B carbon, I already told that we can select any of the overlapped carbon, not only A, we can also select B carbon. Now when we select B carbon and record the spectrum, you can see A carbon is, when we selected B carbon, A carbon is not selective. Non-selective carbon appear as a multiplet. This is A carbon. Now B carbon is selected, appear as a singlet. You can see the first spectrum, the first SFORD spectrum is not useful to predict the nature of carbon. Now the selective proton decoupled experiment, this is the first spectra, it indicated B carbon. Triplet indicated B carbon. Triplet for B carbon indicated it is a CH2. A is unknown. When we select B carbon and B carbon signal appear as a singlet, A carbon is not selected, therefore appear as a triplet. What happens? Now this signal, the triplet related to A carbon, indicated A is also CH2. A carbon is also CH2. You can see these two spectrum indicated A carbon is CH2, B carbon is also CH2. These two spectrums are called as selective proton decoupled spectrums. Now let us study some more examples. You take N-pentanol, CH3, CH2, 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 OH. 2 CH2, 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 2 CH N-pentanol C13 spectrum, carbon A, carbon B, C, D and E carbon. A is a CH3, therefore quartet. It is triplet, triplet, triplet and again triplet, again triplet. So A, B, C, D, E, 5 carbons are there. One carbon appear as a quartet, the remaining carbons appear as a singlet, triplets. It's SF4D spectrum. Now it's SF4D spectrum. A carbon appear as a quartet. A appear as a quartet. E carbon, this is terminal CH2, appear as a triplet. E carbon appear as a triplet. Now B, C, D carbon, because of low frequency difference between B and C and D, their multiplicity triplet, triplet and triplet of D carbon get overlapped. B, C, D. It become complex. Now, because of low frequency difference between B carbon, C carbon, D carbon, their triplet multiplicity lines get overlapped, resulted a complex middle, and the middle portion of the spectrum become complex. Now, when we record by selective proton decoupling method, now in the selective proton decoupled method, now I am going to select C carbon. Select C carbon and record the spectrum. You can see A appear as a quartet, A appear as a quartet, E also appear as a triplet, E also appear as a triplet. Now C signal appear as singlet as it is selected. C carbon is selected, therefore it appear as a singlet. Now B carbon triplet, D carbon triplet. Now this is selective proton decoupled spectrum. A quartet, B triplet, D triplet, E triplet. Now C carbon appear as a singlet. Now this experiment suggested, this experiment indicated that B and D carbon triplets indicated BC carbons are CH2 carbons. BC carbons are CH2 carbons. And B and D carbon triplets indicated these two carbons are CH2 carbons. Whereas in the SF4D spectra, we are unable to predict B carbon, C carbon and D carbon. When we apply the technique of selective proton decoupled experiment, during that C carbon is selected so that C carbon signal appear as a singlet. The B carbon and D carbon signals appearing as a triplet. So their triplet multiplicity indicated B carbon, D carbons are CH2 carbon. C carbon is not known because it is a singlet. Now in the second method, if we select B carbon is selected, D carbon is selected. When we select B and D carbon, C carbon is not selected. Now again if we record the spectrum, if we record the spectrum, you can see a quartet is appear for A carbon. Now B carbon is selected, therefore it is appear as a singlet. B carbon is selective. C carbon is not selected, it appear as a triplet. D carbon is selected, therefore appear as a singlet. E carbon triplet. This is second spectrum. You can see B, when we select B and D carbon, those two signals appear as a singlet. Now this is C is non-selective carbon, it appear as a triplet. Now triplet signal of C indicated it is also CH2 carbon. C is also CH2 carbon. C is also a CH2 carbon. Now these two spectrums are selective proton decoupled spectrums, where the first spectrum indicated B and D are CH2 and the second spectrum indicated C is also CH2. So this is about selective proton decoupled spectrum. Is it clear? Now let us go for another type of C13 NMR spectrums. one. After selective proton decoupled spectrum, we will go for to study the another type of spectrum, that is insensitive nuclei enhancement by polarization transfer experiment. A fifth type of C13 NMR spectrum, insensitive nuclei enhancement by polarization transfer experiment. Now it is also called as multi-pulse technique. Multi-pulse technique. Multi-pulse technique. Now let us discuss why do we study the multi-pulse technique. There are two multi-pulse techniques. One is inept. Now this is abbreviated as inept. It is abbreviated as inept experiment. Insensitive nuclei enhancement by polarization transfer experiment. Let us discuss why do we study this experiment. Now starting the first C13 NMR spectrum, which is fully coupled, where every carbon is coupled with all hydrogen nuclear spin, so that each carbon signal appear as a multiplet with so many number of lines. There is a chance to overlap each carbon multiplicity signals to get a complex NMR spectrum. Therefore, it were recorded by another technique called as broadband decoupled experiment, where all coupling interactions 1J, 2J, 3J, 4J were eliminated and recorded, so that every carbon signal is appear as a singlet. However, it is a simple singlet. However, it is a simple, but some information get lost in the broadband decoupled spectrum regarding the type or nature of the carbon. The carbon may be CH3 or carbon may be CH2, whatever it may be. Therefore, recorded by SFORD technique, where in the SFORD technique, except 1J at every carbon, remaining 2J, 3J, 4J interactions are eliminated and recorded. That is, every carbon is allowed to couple with its own hydrogen. In that way, CH3, CH2, CH, carbon without hydrogen signals appear as quartet, triplet, doublet and singlet respectively. Now that is fine. In few molecule or in few cases, where the frequency difference between the two carbons or any two carbons are too small, then their multiple signals get overlapped in the SFORD spectrum, resulted a complex spectrum, therefore recorded by selective proton decoupled experiment. Now in the selective proton decoupled experiment, any of the overlapped carbon is selected. At the selected carbon, 1J, 2J, 3J, 4J interactions are eliminated. The remaining carbon atoms, only 2J, 3J, 4J are eliminated. Therefore, selected carbon signal is appear as a singlet. The remaining carbon signals appear as a multiplet similar to SFORD. That is about selective proton decoupled experiment. Now, in the to study a molecule by selective proton decoupled experiment require one spectrum to study each carbon. It require n number of spectrum. The experiment require n number of times to be recorded for the study of each and every overlapped carbon. Just now we have seen in the case of N-pentanol. To identify the nature of B and D carbon, we have recorded one time. To identify the nature of the C carbon, we have recorded another time. If a molecule where n number of carbon signals get overlapped, we should record n number of times by process of selection. It requires n number of spectrums. So it is a drawback. Therefore, the C13 NMR spectrums were also studied by multi-pulse technique or multi-pulse experiment. This is also called as 13C spectral editing technique. Multi-pulse may also called as 13C spectral editing technique. Two techniques are included. Multi-pulse techniques has two multi-pulse techniques were included in your syllabus. The first technique is insensitive nuclei enhancement by polarization transfer experiment. In abbreviated form, it is called as INEPT. Now coming to the INEPT principle and INEPT spectrum. Now in the INEPT experiment, now in an organic molecule, there are in general, in an organic molecule, there are two nuclei. One is proton nuclei, other one is carbon nuclei, C13 nuclei. We know the proton nuclei is highly sensitive. It is highly sensitive to the NMR, sensitive. It is highly sensitive to the NMR. It can easily generate its NMR spectrum as its natural abundance is too high together with high gyromagnetic value. Now this all about we discussed in the introductory part of the chapter. Now similarly, the molecule may also contain a carbon spin active nuclei where it is highly insensitive. To the NMR, highly insensitive to the NMR. So within one molecule there are two type of nuclei, a sensitive nuclei, insensitive nuclei. Sensitive nuclei is a proton, insensitive nuclei is a carbon. Why carbon is insensitive? Together with low natural abundance, 1.11% only, and low gyromagnetic ratio value, 1/4 to that of the gyromagnetic ratio of proton. So together lower value of natural abundance and lower value of gyromagnetic ratio make a carbon nuclei less sensitive to the NMR. Therefore, low sensitivity signals are appear from the NMR when compared with the proton NMR. Now this all we are discussed in the introductory part of this chapter, and we also compared the differences between proton NMR and carbon NMR. Now coming to the chapter. Now within the molecule there are two type of nuclei. Say this is the molecule. Say this is carbon 13 nuclei attached by a proton which is sensitive. So a molecule contain a sensitive nuclei and as well as insensitive nuclei. Sensitive nuclei as well as insensitive nuclei or less sensitive nuclei. Now in the INEPT experiment, the magnetic field produced by the sensitive proton. Now within the molecule there is a proton, there is a carbon. A proton nuclei is a spin active nuclei. Due to its spin, due to the spin around its vertical axis, it produced a magnetic field. Now a proton nuclei, it is a highly sensitive nuclei and it is a spin active nuclei. We know it is capable to produce its own magnetic field. Now in the INEPT experiment, in this experiment where the magnetic field produced by a proton nuclei, that is sensitive nuclei, is transferred to insensitive carbon, a magnetic field is transferred. Are you following? Now within the molecule we have a two type of nuclei. One is sensitive nuclei, other one is insensitive nuclei. What is the sensitive nuclei? A nuclei of proton, and insensitive nuclei is a nuclei of carbon. Now existed within the molecule, so that the magnetic field produced by a sensitive proton get transferred to insensitive carbon by the process called as polarization transfer. Polarization transfer. Is it clear? A simple principle. A magnetic field produced by the sensitive proton is transferred to a insensitive carbon by the process is called as polarization transfer. By the polarization transfer, the magnetic field is transferred from proton nuclei to carbon nuclei. That means we are making artificially a carbon. When we transfer the magnetic field, whole magnetic field produced by the proton to the insensitive carbon, what happens? We are making artificially a carbon nuclei, insensitive carbon to sensitive. So we are making this carbon as sensitive. Is it clear? Now when we transfer the whole magnetic field from sensitive nuclei to insensitive, so that artificially we made a insensitive carbon to the sensitive to NMR by the process is called as polarization transfer. What happens? Insensitive nuclei will be enhanced by transferring magnetic field from sensitive proton to insensitive carbon by the process is called as polarization transfer. Hence the technique is called as insensitive nuclei enhancement by polarization transfer, that is inept experiment. When we transfer the magnetic field from proton to the carbon, this will help in two ways. Now this transfer of magnetic field from sensitive proton to insensitive carbon help us in two ways. Number one, intensity of carbon signal increases. Intensity of carbon signal increases. Now in the introductory part we discussed about, due to the low gyromagnetic ratio, due to the low natural abundance, a carbon is insensitive to the new NMR experiment, so that low sensitive signals are appear from carbon. So that because of low sensitivity of the carbon signal, we are unable to integrate the signal to get the number of equivalent carbons in each signal. So that is the drawback or difficulty arised in the C13 NMR. So because of short or low sensitive signal, integration is not possible. Whereas in the proton NMR spectrum, high sensitive signals are appear. High sensitive and intense signals are appeared, where we can easily integrate the signal height to get the number of equivalent protons in each signal. Whereas in the case of carbon, because of low sensitivity of the carbon signal, integration sometimes not possible, so that number of equivalent carbons cannot be get from the signal. So we cannot calculate the number of carbons. Now coming to this experiment, when we made insensitive carbon as sensitive by the transfer of magnetic field from proton, so that the carbon nature become like a proton, that is we are making a insensitive carbon as a sensitive, that will help us to improve the intensity of carbon. When we make a carbon as a sensitive, automatically its sensitivity, the signal sensitivity also increases. So the intensity of carbon signal increases, so that we can easily integrate like a proton signal integration. This is one way it helped. The transfer of magnetic field helped to improve the intensity of carbon signal from the spectrum. Now in the second way, the transfer of magnetic field will also help us to predict nature of the carbon. That is, this transfer helps us to know or study about number of CH3 carbon, CH2 carbon, CH carbon, and as well as carbon without hydrogen. without any difficulty. That is, we can easily predict the nature of carbon or type of carbon within one spectrum without any overlapping multiplicity signals. Even the frequency difference between the carbons is too short. We have just now discussed about if the frequency difference between the two carbon is too small or short, what happens? The multiplicity signals get overlapped in the SFORD. To overcome the problem arised in the SFORD, we have studied the selective proton decoupled experiment, where again another problem is arised regarding the n number of spectrums to be recorded to study n number of overlapped carbons. So to overcome this drawback, we have we have to study about inept experiment, insensitive nuclei enhancement by polarization transfer experiment. Now here, this transfer helps us to predict the type of carbon like CH3, CH2, CH and carbon without hydrogen without any difficulty. We can identify the type of carbon within one single spectrum. No need to record multiple number of spectrums. So within a single spectrum, we can identify. Now here a question arises. Is the signals are not overlapping? No. Not like SFORD. Inept experiment, even the frequency difference between the carbons are too small. The multiplicity signals never overlapped. When the signals are never overlapped, we can easily predict. Even in a single spectrum, we can study the nature of carbon or type of carbon without any difficulty, because the multiplicity signals never overlapped in the inept experiment. Because in the inept experiment, the CH3 quartet, a CH3 quartet signal of SFORD, this is quartet signal of SFORD, is recorded as two positive lines and two negative lines in the inept. This is SFORD, this is inept signals. Now we are discussing about why the multiplicity signals are not overlapping in the inept, even the frequency difference is too short. Because the quartet of SFORD signal will be recorded as two positive line, two negative line in the inept experiment. Similarly, the triplet corresponding to CH2, a triplet corresponding to CH2 of SFORD, this is SFORD, is recorded as one positive line, one negative line with zero intensity middle line. Are you following? A triplet related to the CH2 carbon of SFORD is recorded as one positive, one negative line with zero intensity middle line in the inept experiment. Similarly, the doublet related to CH carbon, a doublet of CH carbon of SFORD is recorded as one positive line, one negative line. This is quartet, this is triplet, this is doublet in the inept experiment. The singlet related to carbon without hydrogen always recorded as positive in the inept. This is singlet. Is it clear? You can see in the inept experiment, the CH3 carbon quartet appear as two positive, two negative line. A CH2 carbon triplet appear as one positive, one negative with zero intensity middle line. A doublet signal of CH carbon appear as one positive, one negative line. A singlet signal related to the carbon without hydrogen appear always as positive line. Is it clear? So this is the pattern of recording of multiplicities in the inept experiment. Whereas in the SF4D experiment, all lines regarding the multiplicity signals are recorded as positive. There is a chance to overlap in the case where the frequency difference between the carbons are too small. As all the lines related to every carbon multiplicity can be get accommodating as a positive, if the frequency between the two carbons is too small or short, a possibility of accommodating all the lines as a positive, a chance to overlap. Whereas in the experiment of inept, where a quartet signal get recorded or accommodating with two positive line, two negative line. Triplet with one positive, one negative line, with zero intensity middle line. A doublet recorded or appearing or accommodating as one positive, one negative line. A singlet always a positive line. So this is the pattern of recording or accommodating the multiplicity lines in the inept experiment. Now in the inept experiment, where the multiplicity lines related to the signals of every carbon is accommodating few of them as positive, few of them as a negative. So when we remove few positive lines and record the same as negative, there is a space is created in the positive line. Therefore the overlapping is removed, or overlapping possibility is reduced. There is no overlapping multiplicity. Now in the inept experiment, always a signal start with positive line and end with a negative line. So every signal in the inept experiment start with a positive line, end with a negative line. After ending a negative line, if immediately starts one positive line, that indicated the signal is related to other carbon. Are you following? So every signal arised with a positive line followed by end with a negative line. After ending a negative line, if immediately there is a positive line indicated, it's a signal related to the other carbon, not first one. So in that way, without any confusion, we can identify the number of carbons with their multiplicities within one spectrum. For example, now example, you can take, just now we studied CH3, CH2, 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 CH2OH, N-pentanol, A carbon, B carbon, C carbon, D carbon, E carbon. A quartet for CH3, triplet, triplet, triplet and triplet, 4 carbons triplet. It's a SF4D spectrum. We have just now studied. A CH3 signal appear as quartet, terminal CH2 signal appear as triplet. This is F. A carbon quartet, F carbon triplet. Now regarding to the signal related to B carbon, C carbon and D carbon, because of low frequency difference, there may be overlapping. B, C and D. Now you can observe B carbon, C carbon, D carbon, 3 triplet signals get overlapped in the SF4D. This is SF4D spectrum. SF4D spectrum. Now if we record inept spectra for the same molecule, if we record inept spectra, you can see what happens. A CH3 carbon signal is a quartet. It is recorded with 2 positive line, 2 negative line. A carbon signal, 2 positive, 2 negative, a quartet. B carbon is recorded with 1 positive, 1 negative and 0 intensity middle line. This is B carbon, as it is a triplet. C carbon is also triplet, recorded with 1 positive, 1 negative, 0 intensity middle line. This is C carbon. Similarly, D carbon, one positive, one negative line with zero intensity middle line, it is related to D carbon, triplet. F carbon, one positive, one negative, zero intensity middle line, F carbon. Is it clear? Now this is inept spectrum. This is inept spectra. You can see where in the SFRD there is a overlapping, unpredictable. B, C, D carbons are unpredictable due to their overlapping. Now coming to the inept experiment, where a quartet is recorded with two positive, two negative line, a triplet with one positive, one negative, zero intensity middle line of B, and C is also one positive, one negative, zero intensity middle line. D carbon, one positive, one negative, zero intensity middle line. Similarly, F carbon, one positive, one negative line with zero intensity middle line. Is it clear? Now you can see, I already told that every signal starts with a positive line, end with a negative line. So after the negative, ending the negative line, if immediately there is a positive line in the spectrum, indicated it is other carbon, a signal or line is related to the other carbon, not to the first carbon. You can see two lines started, two line ended, a quartet. A is a quartet, A is CH3. Now here B carbon starts with positive line, end with negative line, with leaving zero intensity middle line, indicated B carbon is a triplet. C carbon, one positive, one negative, zero intensity middle line, C carbon indicated is a triplet. And D carbon, one positive, one negative, zero intensity middle line. So start with positive line, end with negative line. D carbon is also a triplet. Now B carbon, C carbon, D carbon, three triplets indicated. B carbon, C carbon, D carbons are CH2 carbons, where this information is unpredicted from the SFRD. B is unknown, C is unknown, D is unknown. But in the inept experiment, we can identify B appearing as a triplet, C appearing as a triplet, D is also appearing as a triplet. So the three triplet, B, C, D triplets indicated, B carbon, C carbon, D carbon, all the three carbons are also CH2, belongs to CH2 carbons. Now this information, the same kind of information is unpredicted. It is not possible or unpredicted from the SFRD experiment, where the B and C and D carbon signals get overlapped. Because of overlapping, they are unpredictable. So we can predict the type or nature of the carbon based on the number of lines in their multiplicity. When the multiplicity is overlapped, when we are unable to predict the number of lines, so we are failed to identify the nature of carbon. Now coming to the inept experiment, the same carbon signals, because of recording few lines as positive, few lines as negative, the complexity or overlapping get removed or eliminated, so that we can easily predict or identify the multiplicity. B is a triplet, C is a triplet, D is a triplet. When we able to predict its multiplicity, we can able to predict the type of carbon. When it is triplet, it belongs to CH2. Is it clear? So B triplet, C triplet, D triplet indicated B, C, D carbons belongs to a CH2 carbons. Is it clear? So this is about inept experiment. No need to go for selective proton decoupled experiment, as within the single spectrum we are able to predict. Is it clear? Now let us go for few more examples for inept. CH3 O C double bond O CH2 CH3. Now this is the molecule. Now this is A carbon as quartet because it is a CH3 carbon. This is B carbon again as quartet. B is also quartet. Now C carbon is CH2, hence its multiplicity is triplet. Now these two carbons, A and B and C carbon, the two ortho carbons with respect to methoxy. Methoxy is electron releasing group, therefore upfield. D carbon. Now it is a CH carbon, therefore multiplicity is doublet. Two orthocarbons are equivalent and upfield when compared with meta, because these two are ortho with respect to methoxy group, where methoxy is electron releasing. Now the two remaining carbons are ortho with respect to keto group, which is electron withdrawing group, therefore downfield E carbon. Now E carbons are also belongs to CH carbon, therefore doublet. Now carbonyl carbon is F carbon. It not bearing any hydrogen, it is appear as a singlet. Now it's inept spectrum. Is it clear? A, B, A carbon, B carbon. This is CH2 is a C carbon. Two orthocarbons are D carbon. Two E carbon, metacarbons belongs to E and doublet. Carbonyl carbon is singlet, that is F carbon, it is singlet. Now it's an inept spectrum. A carbon quartet appear with two positive line, two negative line. A carbon. And now B carbon is also quartet. Two positive line, two negative line. B carbon is also quartet. Now coming to C carbon, it is a triplet. So that one positive line, one negative line with zero intensity middle line, C carbon. Now D carbon is doublet. So that one positive line, one negative line for doublet. E carbon is also doublet. One positive line, one negative line. E carbon, doublet. F carbon is singlet. Singlet carbon always appear as positive. This is inept spectrum. Inept spectrum of the molecule. You can see, we can easily study the nature. Two positive, two negative lines, one signal. Two positive, two after negative line, if there is a immediate positive line, indicated the other carbon. Two positive, two negative, one signal. Two positive, two negative, second signal. One positive, one negative, zero intensity middle line, third signal. One positive, one negative, fourth signal. One positive, one negative, fifth signal. This is sixth signal. So there are six carbons. There are six carbons or equivalent sets of carbons. Now two carbons are CH3 carbons, because quartet and quartet. Two carbons belongs to CH3 group. One carbon is CH2 because it is a triplet. One carbon is CH2. Two other carbons doublet indicated, they may be CH group. Now this singlet indicated one carbon without hydrogen. So in this way we can easily interpret the inept experiment to get the information. Now we will discuss another example. Now this is the molecule 1 2 3 1 2. Now this is 1 2 3 4 5 6 1 2 3 hexanone. This is A carbon, this is B carbon, this is C carbon, this is C carbon, this is D carbon, E carbon, F carbon. A carbon quartet, B carbon quartet, C carbon triplet, D carbon triplet, E carbon triplet, F carbon singlet, because there is no hydrogen. It's an inept spectrum. It's an inept spectrum. A quartet, two positive line, two negative line. A quartet. B quartet, two positive line, two negative line. B quartet. Now C carbon triplet, one positive, one negative, zero intensity middle line. This is C carbon. D carbon is also triplet, one positive, one negative, zero intensity middle line. D carbon. E carbon is also triplet, positive, negative, zero intensity middle line. E carbon. F carbon is singlet. F carbon is singlet. This is about inept spectrum. Inept spectrum for 3 hexanone. 2 quartets indicated, 2 CH3 groups. 1, 2, 3. 3 triplets indicated, 3 CH2 groups. 1 singlet indicated, 1 carbon without hydrogen in a molecule. The number of carbons are 1, 2, 3, 4, 5, 6. So there are 6 carbons. Among the 6 carbons, 2 belongs to CH3, 3 carbon belongs to CH2, 1 carbon belongs to carbon without hydrogen. So this is about inept spectrum. Now you can see a simple molecule, chlorobromoethane. Chlorobromoethane. Now it's SF4D. There are 2 carbons, A carbon, B carbon, A triplet, B also triplet, AB triplets. Now if we record its SF4D, we can observe there is a overlapping. We can observe there is a overlapping, that is a complex. So this is not useful. For the same molecule, if we record its inept spectra or go for inept experiment, now A carbon is a CH2, hence its multiplicity is triplet and appear as a 1 positive, 1 negative with 0 intensity middle line, A carbon. B carbon is also CH2, hence its multiplicity is also triplet, appear immediately with 1 positive, 1 negative line, B carbon. You can observe the difference between the 2 experiments. One is SF4D. This is SF4D experiment. SF4D experiment. This is inept experiment. Inept experiment. We can observe. If we accommodate all the lines as positive, because already the frequency difference between AB carbons are too small due to the similarity in their electronegativities. So when the frequency difference is very close to each other or too small, if accommodate the 2 triplet signal as a positive, there is a overlapping. Now in the inept experiment, within the same space, same frequency difference between the 2 carbons in the case of SF4D as well as in the case of inept experiment. Now however, when we accommodate few lines of the triplets as negative, few other as positive, there is a space is created. There is a space is created. Now in the first experiment, in the SF4D experiment, 2 triplets belongs to 6 lines. The 6 lines are overlapped. Now out of 6 lines, now coming to inept experiment, out of 6 lines, 2 lines intensity become 0, left over 4 lines. Are you following? There is a 6 lines in the SF4D belonging to 2 triplets of 2 CH2 carbons. Out of 6 lines, 2 line intensity becoming 0, that is middle line intensity becoming 0. So out of 6, when the 2 line intensity becoming 0, the leftover lines are only 4. Now among the leftover lines, 2 lines are recorded as positive, 2 lines are recorded as negative. Therefore a space is created. So you can see within the same space, within the same frequency difference between AB carbon from here to here, coming to SF4D to inept, the overlapping is removed. Are you following? A simple technique. How overlapping is removed? Because out of the 6 lines, 2 line intensity becoming 0, the leftover 4 lines will be recorded as 2 positive and 2 negative. When we remove few lines from positive to negative, shift from positive to a negative, what happens? A space is created. So we can easily identify positive, negative, one signal. Immediately after negative, immediately a positive line started corresponding to the second carbon not belongs to the first one. So positive, negative, one signal, immediately positive and negative second signal. So a molecule consisting of 2 carbons, both are corresponding to CH2 because both the signals are appearing as a triplet, positive, negative, 0 intensity middle line, positive, negative, 0 intensity middle line. So The two triplet signals indicated two carbons are CH2 carbons. Now in the SFRD it is unpredictable. In the inept experiment we can easily predictable. So this is the advantage between SFRD experiment to inept experiment. So inept has many advantages over the past techniques which we are discussed, like fully coupled spectra, broadband decoupled spectra, SFRD spectra, selective proton decoupled spectra. Over all the spectrum, all the kind of techniques, the inept has many advantages. However, has many advantages. It also associated with few drawbacks which we should discuss in the next experiment, that is depth experiment, distortionless enhancement by polarization transfer experiment. So with this I conclude today's lecture. We will discuss the leftover experiment, the types of C13 NMR spectrums, followed by the another topics of the chapter in the next lecture. Thank you very much.